right, everyone. Welcome back from the break. Hope you had a good time. Um, I guess um, after the break, we're gonna switch gears a little bit and talk about this new method, um, which is all again related to computations, meaning more MATLAB programming. Um, but since I'll be giving you the codes and I'll be explaining these topics in class, you should be able to relate what we are covering with the MATLAB codes. Couple of, I guess, um, administrative things. I do have your quiz 3 mostly done, but not quite completed yet, even though it was a long break. But you should get it back on Wednesday. Um, and we'll be posting homework 7, I think, today. Pretty much, pretty much all on the computer methods that we had talked about in the week previous to the spring break. And then I think next homework is going to be all on this stiffness method that we'll start today. And that's basically what's going to be on the last quiz 4. That's, I think, in, is it 2.5 weeks from today? I think this week, next week, and then the following week is the quiz 4. All right, so any questions or any concerns before we jump in back into structural analysis? How many of you got a chance to look at the MATLAB code for the previous sections that I posted? Nobody? Okay. A few of you looked at. I'm sure the homework is going to make you do that. And of course, I'll be available for questions. I'm sure there'll be lots of questions. So, okay, what we'll do today is do a very quick review of the MATLAB codes and actually the force and flexibility method for which I gave you the MATLAB codes, and then we'll jump into the stiffness method. So a while back, I reminded you of these two different methods of structural analysis that we commonly use. One is the force method, where we, for an indeterminate structure, what we do is we find an underlying determinate structure, then we find the flexibility of the redundant degrees of freedom, and then use compatibility to solve for those redundant degrees of freedom. And if you remember from our discussions and even from the MATLAB code, normally we end up getting a system of equations that we have to solve for the redundant unknown forces. We are solving for forces in the force method. And actually, technically, even the method of joints for trusses is a force method. We are solving for forces there, but since it's a method of joints for determinate trusses, it's you don't need compatibility or anything. You can solve it purely based on equilibrium. It's not usually a problem. As opposed to the force and flexibility method, we have this method called the displacement or stiffness method. And most, if not all, of the structural analysis codes, structural analysis software that you might actually end up using when you graduate and go to a firm and do structural analysis will likely be based on displacement or stiffness method. And some of you who might have actually heard of the finite element method, that also falls in this category of displacement and stiffness methods. In contrast to this force and flexibility method, the displacement method, the logic is quite a bit different. The idea really is that we can think of any structure as an assembly, as an assembly of components. So if I have a truss, there are lots of truss members in there. Some members are in compression, some members are in tension. We think of the truss as an assembly of those members. And the idea is that if we can figure out how each truss member behaves, meaning if I have a truss member in a certain orientation in space, then if I can figure out what is the relationship, what is the force displacement relationship of this one element, then I can do that same force displacement relationship for every other element in that truss and assemble the force displacement relationships together and then use equilibrium to solve for all the displacements directly. Okay. Here, you'll also end up getting a system of equations that looks like KD is equal to F. K is being the stiffness matrix, D being the displacement coefficients of all the degrees of freedom in the structure, whether it's a truss or a frame or whatever, and F being the external forces being applied to the structure. One good thing about this method is that you get displacements directly. You're actually solving for the displacements at all the degrees of freedom of the structure. If you remember back here, we were solving for internal forces. Once we got internal forces, how did we get displacements? Anybody remember? For the mass? Right. So we had to find the internal forces among all the members, and then to go to a specific node, find the displacement, x and y displacement, we applied a unit load, and then again recomputed the virtual displacements for each and every node. So it's a big task back there to find displacements, displacements of each and every node in the structure. Here we directly get those displacements. We do have to do some little bit extra work to find internal forces in the truss or in the structural members, but that's not as bad as doing a virtual work method here. Another good thing about this displacement and stiffness method is that it doesn't care whether your structure is determinate or indeterminate. It's exactly the same method. No changes, no redundancies, no nothing to calculate. It's exactly the same method that you would use to solve a determinate truss or an indeterminate truss. And therefore, it happens, well, it's quite easy to program in a computer, the program which I will actually give you, and again, expect you to be able to use it and to make small modifications to it as needed. All right, so that's sort of the setting in which we are going to talk about the displacement method versus the excuse me, the force and flexibility method. Here's an example of what I'm talking about when we are talking about decomposing a structure into its elements. So here is the exact same truss that we had back in the force and flexibility method. If we want to solve it with the displacement method, we are going to again divide it up into its members and nodes, something you're familiar with. There are 7 members in this truss, right, up to G. So all these members I've denoted with these alphabets, and that there are 5 nodes in this truss. So 7 members, 5 nodes, and I've connected them. There's support conditions, which makes it indeterminate. But as I said, determinate or indeterminate, it does not matter for the stiffness method. Now, the key idea here is if I look at a particular member, say this member C, which is connected to nodes 2 and 3. Excuse me. That member in the deformed configuration can will displace in general at both ends. At 2, this node 2 might go somewhere here. This node 3 might moves down. And what I'm showing you here is that from the original configuration, a particular member M that is connected to nodes I and J will move to a new location that's shown in the blue configuration. So the black dotted or dashed line is the old unloaded position of the member. When I apply the loads, then the member moves, both ends, they move to this new location. And the whole idea is that if I can somehow relate the force in this member, which technically can only be in compression or tension, so I'm marking it as Fm, denoting M denotes the member or the element number. If I can relate that Fm to the delta x displacement and delta y displacement at node I, and the same delta x and delta y displacements at node j, then I have something that that I can use as a force displacement relationship for this particular member, for one particular member in the truss. Okay, so that's what I mean by force displacement relationships. If uh, if you tell me what is delta x, what is delta y at node I, and what is delta x, delta y at node j, then I can tell you what is the force in the member. Does that make sense? If I have a truss member, I tell you that it's connected to two nodes I and j. I'm moving node I by some amount in the x, some amount in the y, same thing for j. Then I know what the final configuration of that member is. I know how much it has extended, right? By knowing how much it has extended, I will immediately know what is the internal force in that member. And if I do that same logic for each and every member in that truss, and then finally be able to add all the forces at among all these members. So for example, at node 2, there's member A, C, D, E, all connecting to node 2. They will all exert their forces to node 2, and then I can use equilibrium for node 2 to calculate what displacements node 2 should have. So that's sort of the overall logic. What we are going to do is to try to develop this force displacement relationship for truss members, and then we'll extend that same logic to frame members, beam problems, and in general to actually composite structures or any type of structure. All right, so let's take a look at what we need in order to do that. We need geometry of the problem. Geometry of the problem is something that we've seen before with the force method as well. Node locations. I have 5 nodes in here. There are these 5 nodes. I'm marking the locations. This is very similar to the MATLAB input file that we used for one of the truss problems. X and Y coordinates for each of those nodes. That's, of course, needed. We also need the member connectivity. There's 7 members. They're each connected to 2 nodes. And the ordering does not matter. 1 is connected to 2 or 2 is connected to 1. It's the same thing. But when we are doing transformations, you do have to keep track of ordering, and when we are assembling those matrices, as we'll have to keep track of this ordering. For the stiffness method, there is something called degree of freedom, which, as intuitively you might think of, it's basically an unknown displacement that you want to solve for. So degree of freedom, sometimes people also call that as kinematic indeterminacy. What we were talking about indeterminacy before in the force method was force indeterminacy, right? Here for this structure, you remember what the force indeterminacy was for this structure? Anybody remember that? Two, yeah. So if I remove this support, then it becomes determinate. So clearly, if the reactions 5x and 5y, if you remember, we call those redundant reactions. That was force indeterminacy of 2. Now what we are talking about is a degree of freedom, meaning kinematic indeterminacy. The way we determine that is go to each node and see if that displacement is known. So at node 1, both x and y displacements are 0. They're known. At node 2, both x and y displacements are unknowns. So we have 2 kinematic indeterminacies right there. We have node y displacement unknown, x and y unknown, and x and y known here. So total of 2, 2, and 1. 5 is the degree of kinematic indeterminacy for this problem. Okay, this is different from the force indeterminacy, but I think you intuitively understand that this is a degree of freedom for the structure to be able to move in that direction. So in general, for truss problems, for each node, we'll have 2 degrees of indeterminacy or degrees of freedom. And unless it is fixed, right? Unless it's fixed in one or both of those directions, we'll have 2 degrees of indeterminacy. And the way we handle that is by actually just assigning degrees of freedom to each node. Node 1 has degrees of freedom 1 and 2. 2 has 3 and 4 and so on. So you should be able to see that 1 and 2 here, 2 has 3 and 4, node 3 has 5 and 6 and 7 and 8 and 9 and 10 and so on. In general, if you have n nodes, how many total equilibrium equations will you have? 2n. And that should be equal to the number of unknowns if it's a determinate problem that you're trying to solve, right? 2n total number of unknowns, including all the reactions and all the internal forces if it's a determinate problem. Now, you remember even for the force and flexibility method, we assigned that for a particular node, the degrees of freedom would be what? If I give you node I, what would be the degrees of freedom associated with it? Say, for example, for node 3, degrees of freedom associated are 5 and 6. So if it's a node I, maybe I'll write that here. For node I, what would be the degrees of freedom? Drew? Say that again? There would be both x and y displacements for a general node. But for example, I'm saying node 3 here. This node 3 has a degree of freedom 5 associated in the x direction, 6 associated in the y direction. For 4, it's 7 and 8. So if I have a big, huge truss with hundreds and hundreds of joints, then I go to a particular joint number I, what would be the 2 degrees of freedom associated with it? 2i minus 1 and 2i, right? And that's going to be really helpful when we are looking at the MATLAB code for this. So 2i and 2i minus 1 would be the degrees of freedom associated with node I in general. That's just a numbering scheme that we are choosing. And so among all of those degrees of freedom, as I said, some of those are free degrees of freedom, meaning they are free to move. And some of them are specified degrees of freedom, meaning they are fixed, they cannot move. So in this particular problem, what are the free degrees of freedom? 2, right? So if we go to node 2, 3 and 4 are free. So 3 and 4 are free. And node 3, which degree of freedom is free? 6. 6 is free. 5 is fixed. All right, so we'll add 6 there. And 7 and 8 both are free at node 4, and 5 both are fixed. So let me also write the specified or the fixed degrees of freedom. So there would be 1, 2, 5, and 9 and 10. So this is an exercise that is just describing the problem. All we have done till now, we have described the problem that there are some nodes, some connectivities, and there are some free degrees of freedom, and there are some specified degrees of freedom. And we've still not specified that where the load is acting, but that is something that we'll do exactly the same way that we did with the force method. Here, node 4 has a vertical load of minus 10 kilonewtons. Node 2 has a horizontal node of 10 kilonewtons. So that's just the description of the problem. Now what we want to do is, using this description, we want to come up with force displacement relationships for each one of those truss members. And in order to do that, we are going to have to work with a few two different coordinate systems. Okay, the need for these 2 different coordinate systems is because all of these truss members are actually oriented along different directions, right? So if I have a truss member, say, oriented at a 45-degree angle, then I know that if I extend it along that direction in that axis, then I will create additional, or I will need to apply internal forces to the truss member, right? Instead of trying to extend it in this direction, if I move it perpendicular, a little bit perpendicular to the member itself, will I create any forces? If I have a truss member, let's say horizontal here, okay, and if I move one of the nodes a little bit up, does the truss member come into any tension or compression? Assuming that the displacement is really small, negligible in comparison to the length of the truss member, that does not create any forces, right? If I move it quite a bit up, then then we would have to account for that length, change of length, and that it would come into tension. But that's an assumption that we've already made, that we are talking about small displacements, linear problems, okay? So the reason that we have to work with these two different coordinate systems is because all of these truss members are oriented in all different directions. So one coordinate system will be the global coordinate system, which I'll draw as here. So just an X, Y global coordinate system. This global coordinate system we will use to sum up all the forces from all the truss members. You remember the way we are going to do it is find force displacement relationships and sum them up in a global coordinate system. The other coordinate system that we are going to use is the local coordinate system, and it will take me a little bit extra to draw this. So what we'll do is, for example, we'll go to node J. We'll draw the global coordinate system, and then I'm going to rotate it to match it with the local coordinate system. The local coordinate system is always oriented along the member. So for member M that's connected to nodes I and J, the local coordinate system looks like this. I'm going to call that X prime and Y prime. Same thing here at node I. So let me copy that. And at node I as well, I'll have X prime and Y prime. So the global coordinate system I'm calling vertical and horizontal as X and Y. The local coordinate system will be attached to each and every member. So if the member is oriented in a different direction, here I'm showing you it's oriented kind of almost like a 45-degree angle. If it's a 30-degree angle, it will be oriented along the 30-degree angle. If it's a negative 45, it will be oriented along the negative 45-degree angle. So it's just the local coordinate system is always attached to the particular member we are talking about. And we need both of these to be able to find our force deflection relationships. So here's another thing that we're going to need. We're going to need to be able to transform vectors, whether it is displacements or forces, between these two coordinate systems. Okay. Now the idea is that given some vector v, this vector v that I'm showing you in red, a vector is an abstract quantity. It does not depend upon your choice of coordinate system. Okay, so here's the key concept that you need to understand about vectors. Let's say I tell you that there is a vector from that corner of the room to that corner of the room. It's an abstract definition of a vector. It will always be pointing from that corner of the room to that corner of the room. It has some magnitude, it has some direction. That's all. That's what a vector is, right? A vector is nothing but a magnitude and a given direction. Now, one of you comes up and says, I'll pick my coordinate system right at the bottom of this corner and orient it along, say, X, Y, and Z. And in that coordinate system, I can say that this vector would be, say, 10 meters X and 5 meters Z, right? So 10, 0, 5. Now somebody else might come along and say, no, I don't like this coordinate system. I'm going to use a different coordinate system, a local coordinate system. I'm going to orient myself in this weird direction, and then I'm going to calculate the components of that vector. Neither one of them is wrong, right? Both are correct. They are just different descriptions of the same physical quantity. So we have to be able to move or relate these two descriptions of a vector. So that's what this vector is showing. This is a physical abstract vector quantity. It has some magnitude, some direction. If I choose the global coordinate system x and y, then the components of that vector would be vx and vy, right? Somebody else comes along and says, no, I want to use this x prime and y prime coordinate system. In that x prime and y prime coordinate system, that the components would be vx prime and vy prime. And we have to be able to correlate how we can find vx and vy with vx prime and vy prime. And that relationship between these two coordinate systems is basically what we call transformation of vectors between global and local coordinate systems. This is something that I'm sure you have done before, but I'll show you somewhat of an easy way to do this. Let's see how to go about this. In particular, what we want to do is we want to transform displacements or forces that are associated with some member M um, from its local coordinate system to the global coordinate system. That's what we want to do. So first things first, we'll have to figure out some basic geometric relationships. If this member is oriented along some direction, I can find its angle with the horizontal axis. That's what I'm calling theta x, or simply theta. So cosine of theta x, can I calculate that knowing that the x and y coordinates of node J are xj, yj, and x and y coordinates of node I are xi, yi? What would be cosine theta x if I know the coordinates? And maybe just to help you, I'll draw a few dotted lines as well. So how can I find theta x? Yicheng?
Cos.
Yeah, how do I find cosine theta x?
Oh, okay. That'll be
Base divided by
the
hypotenuse, right? So hypotenuse is the length of the element. That's I've calculated here. Hopefully you all can see that the length of the element would simply be xj minus xi squared plus yj minus yi squared, right? So denominator will be L. So I'll put that here. And what would be the numerator reaching?
The numerator is x distance.
Xj, right?
Oh,
Yeah, xj, because of course this point has the same x coordinate. So xj minus xi would be this length. And I'll write that here, xj minus xi. And basically, purely from the description of the problem, xj and xi are known to me, right? You remember we talked about this nodal description. So for example, for 2, 3, node 2 has x component 3, node 3 has x component 0. So if I do 3 minus 0 divided by 5, that's the cosine theta of that angle. That's exactly what we are doing here. Cosine theta x is xj minus xi over L. Cosine theta y would be, since this is also theta y, this would be this length divided by the hypotenuse, which would be simply yj minus yi over L, right? Just geometry. And what we are going to do is I'm going to call this cosine theta, and I'm going to call this sine theta. And if you look carefully, if I put them in a vector of 2 cross 1 vector, can anybody tell me uh, in what direction is this vector pointing? This is a unit vector, first of all. You should be able to see that. If I square the components, of this vector, cosine square plus sine square theta, that should be 1. So it's a unit vector. Now, in which direction is this vector pointing? It's pointing from node I to node J, right? X component is cosine theta, Y component is sine theta. So it is a vector that points in this direction, and I'm going to call it nm hat. So n denotes a unit, n hat denotes a unit vector. M denotes the fact that it's associated with element m, and it's always pointing from node I to node j. If I switch the order connected from of connectivity, say, then the vector from j to I would just be negative of that. Okay. Now another vector that we'll end up using. So here's the question: why did I calculate this vector? This nm vector, in which direction is it pointing? It's pointing along the x prime axis. That's why I wanted to calculate the vector from I to j that points in the x prime coordinate system. Okay, this is going to help us correlate these two coordinate systems. The other vector I need is something perpendicular to this member, so in this direction. And purely from geometry again, you will be able to see that if I call that m hat m, then m hat m, let me call this first n hat m, and a vector m hat m would be minus sine theta and cosine theta. So these are two vectors. If I both of these vectors I can calculate easily based only on the node locations. So these two vectors are going to help us correlate the local and the global coordinate systems. So let's see how we can do that. Back to this diagram. If I have a vector v, I want to find vx and vy. I want to find the relationship between vx, vy and vx prime, vy prime. So first to vx. Just looking at this geometrically, if I want to calculate the x component, I hope you can see that that x component would be equal to this length vx prime cosine theta. So if I drop this down, that would be the x component and minus vy prime sine theta. So let me write that first, and then we'll make sure we agree with that. So vx prime cosine theta and plus vy prime times minus sine theta. I hope that this is something that I'll have to ask you to convince yourself with geometry that this is a valid relationship. Vx is the x component for vx prime, and subtract out the x component for vy prime. You'll get this relationship. Okay, the same thing for vy. If I do vy prime, then I'll have to take the y component of vx prime. So I'll write that as vx prime sine theta plus vy prime cosine theta. Okay, because for the y direction, both vx prime and vy prime are contributing positively. So there's not a negative sign here. And this type of a relationship is very easily expressed in the form of a matrix. I can write that as cosine theta minus sine theta, and cosine theta. And by the way, if you haven't noticed yet, the local coordinate quantities I'm writing in purple, x prime, vy prime, and the global coordinate quantities I'm writing in blue. So the local are in purple, the global are in blue. So this is a simple relationship that allows me to calculate what would be the global Vx, Vy, if I know what the local Vx prime, Vy prime are for any vector, whether it's a force, displacement, velocity, acceleration, whatever, vectors just transform in the exact same way, right? Whether it's a vector from that corner to that corner or any other vector. Now, here's a question. If I want to find the inverse relationship, meaning if I know the global coordinate components of a vector, how can I find the local components? How would I do that? Looking at this relationship, if you tell me what Vx prime, Vy prime are, then just by geometry, I know what cosine theta and sine theta are. I'll just take this matrix, multiply with 2 across one vector, I'll get the global components, right? If I want the inverse thing, if I want uh, Vx prime, Vy prime in terms of the global coordinates, what should I do? Right, yeah, so we just take the inverse of that matrix. I'm going to call that matrix T for transformation matrix. And the inverse of this matrix, anybody knows what that is? So this is go ahead. so, so this is a special kind of a matrix that's called an orthogonal matrix. For orthogonal matrices, the inverse of a matrix is its transpose, right? Because this matrix, by the way, what's the determinant of this matrix? What's the determinant of this matrix? Cosine square minus sine square theta. So cosine square plus sine square, that's 1. So that's really easy to invert. And this is an orthogonal matrix. So its inverse is simply its transpose, which means I keep the diagonals as it is and just move the off diagonals to their other positions. So that's T transpose, and actually I'll also write that this is T inverse equal to T transpose. And on the right hand side, then I have Vx, Vy. So using these two relationships, I can find any vector in any of those coordinate systems. If you want global coordinates or local coordinates, using these two relationships, I can find those components for any vector. Okay. All right. So that's still just building the basic blocks of that force displacement relationship. Now let's get into that force displacement relationship. Essentially, what we want to do is, given the original position of the member, that's here in the black solid line, when I apply the loads, the member moves and deforms. So this node I goes to this location, this node J goes to this location. I'm denoting those two vectors as this delta I vector and this delta J vector. Okay, both of these delta I and delta J have two components, delta IX, delta IY, and delta JX, delta JY. So the idea here is, how do I relate this force in the member to these two displacements? Any thoughts on that? How can I, if I'm telling you, here's my original undeformed truss member, and after deformation it extends and maybe moves a little bit to that new blue configuration. I'm also telling you that the displacement vector for node I is that delta I, delta J for J. Using that information, how can you find out Fn? How can you find out what would be the force in that member? Any thoughts, April? Okay, yeah, I think that's exactly what we're going to do. How do I find the strain, first of all? So yeah, one thing to note here is that Since both of these displacements are vectors, I can find their components in the local coordinate system, right? So in the local coordinate system, this delta I would have some component along this x prime and y prime. Similarly, delta J would have some component in the x prime and y prime. Here's the first question. Does delta I y prime and delta J y prime, do they contribute to the forces? Do they contribute to this force M? Just like we talked about a little while ago, if I have a horizontal truss member, if I move it up by a little amount, it does not contribute, right? So delta delta I y prime and delta J y prime do not contribute to that force. The only contribution comes from delta I x prime and delta J x prime. So if we can find those two, then we are in business. And indeed, the change of length is simply delta Jx prime minus delta Ix prime. Hopefully you can see that. If I have, and maybe to see that, what you really need to do is um, to take your frame of view and kind of twist it along the local coordinate system. So if you modify your frame of reference to your local coordinate system, then you should be able to see that displacement here minus displacement here would be the change in length of that member, right? And once I have the change in length of that member, then we know that for any truss member, the change in length divided by L, that's the strain, multiplied by area of cross section, and the Young's modulus is the force. So the local force displacement relationship for a truss member is really easy. That if you give me delta I and delta J as vectors, I'll take the x prime components of those vectors, and simply using those x prime components, I'll be able to find the force in that particular member. Then I have to go to a different member, which might have a different orientation. Then I'll have to do the same thing again for that member and keep on doing that for all the members in my truss. And hopefully you are seeing a pattern here already. So we'll put a loop around all these elements and do this exact same thing for all those elements and then add them together. That's sort of how we are going to proceed. But let's first try to correlate it with with the degrees of freedom or the kinematic indeterminacies of the element. We've just said that Fm, the force in the member, is going to be equal to AE over L times delta L, which is nothing but minus delta Ix prime plus delta Jx prime. The reason I'm writing it in this way, it'll be clear very soon. Hopefully you all agree that 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 this relationship is correct. Now to to generate the local member force displacement relationship for this element, what we are going to do is write first of all the forces at the two ends of the member. So forces at node I are, what are the components of the force at node I? This is Fm in the negative x prime direction, correct? There's nothing in the y prime direction. So if I gave you a vector which is pointing in the negative x prime direction, meaning say say if this my finger here is the x prime direction, this is the y prime direction, and the force is pointing in the negative x prime direction, then how would you express the components of that vector? Negative Fm and 0, right? Negative Fm and 0 would be the force. So I write that here. Negative Fm and 0. That's the force components in the local coordinate system at node I. Okay. The force components at J, what would those be? Fm and 0, right? So, and I'm missing an M there, so Fm and 0. So the force components at node I and node J, They have x prime and y prime components, and I want to relate those force components with these degrees of freedom. What are these degrees of freedom? Hopefully you are already able to see that. Displacement at I and displacement at J. We just said that the displacement in the y prime direction does not contribute. So what does that mean for this matrix? If this matrix is what I'm trying to come up with. If displacement in the y prime component does not affect the force, then would it be okay to say that the second column is all zeros and the fourth column is all zeros, right? Because if I take that column, multiply it with that, take that row, multiply it with that column, then this zero multiplies this guy, this zero multiplies this y prime, right? And how about Ix? What should be here? Looking at this relationship up here. Looking at this relationship, what should I put here? This number is going to multiply delta Ix prime, right? So delta Ix prime has a minus, meaning it should be -1, and this one should be +1. So you can see immediately that sorry, it should be the other way around because this is a minus here. So and the second row is all zeros, so I'll keep these zeros. The third row would be, the third row is actually what we should look at. Fm, this Fm is equal to Ae over L as it is, minus delta I x prime, so this would be 1. Sorry, what am I doing? Need to wake up. Okay, so this should be +1, this should be -1, sorry about that. This should be -1 and this should be +1. So the local force displacement relationship for any truss element, I don't care what truss element, which orientation it is, what is the orientation of that element, how long it is, how short it is. For any element, the local force displacement relationship is this simple. I can tell you what the forces at node I and j would be if you tell me what the displacements at node I and j are. And the reverse thing also, if I tell you, well, actually this is not a full, this is not a, this is a singular matrix, so you can't tell the reverse just by inverting it. But we don't actually need to invert it. What we'll do is we'll come up with this relationship for all the elements in the truss, and then be able to use use equilibrium to solve for all the displacements. So a couple of definitions here. Member forces in local coordinate system. So the coordinate system is extremely important here. You have to keep track of which coordinate system you are working with. Right now, which coordinate system have we been working with? Local, right? Meaning we orient along the member. And this stiffness matrix is what relates displacements to forces. That is also in the local coordinate system. These displacements are also in the local coordinate system. And that's why I'm calling this relationship as Q. The forces for member M, they actually consist of Qi prime, Qj prime. Maybe I'll write that here. So this is Qi prime. This is a 2 cross 1 vector. Qj prime. This is again a 2 cross 1 vector. That vector is what I'm calling Qm prime, a 4 cross. This Qm prime is a 4 cross 1 vector, which is composed of two 2 cross 1 vectors. Similarly, the stiffness matrix in the local coordinate system is 4 cross 4. Why 4 cross 4? Because there are two nodes, there are 2 degrees of freedom at each node. So 4 cross 4. Same thing for displacements. It's a 4 cross 1 uh, vector with two 2 cross, um, I think just to be consistent with that, I'll mark it as delta I vector, delta J vector. Both of those vectors are 2 cross 1 vectors, and I'm calling that delta M prime. Okay. All right. So let's stop here, and then I'll continue this discussion about stiffness method next time. So see you all on Wednesday.